there's something like 36 beams or 40 beams there as per the requirement. So the bandwidth, I am able to accommodate more and more bandwidth, more and more power, more and more my frequency bands in a particular specific area, and thereby I am helping the wireless communication by giving a more this bandwidth requirement. I am able to fill over the Indian region. Earlier I was giving only 1 Gbps, and now I am giving the nearly 32 Gbps. So this is what antenna engineer can do to help to take care of the challenge of a high throughput satellites or giving a high bandwidth. Similarly, for microwave sounders or radars, you must have read radar. So when we are talking about radar, the gain very important because it's a two-way, the transmitter and receiver, same, and the case of monostatic. So this is all the journey of a microwave sounders and radars, where we have various varieties of types of antenna technology used: phase array antenna technology, high gain reflector antenna technology, scanning antenna technology, and then we talk about quasi-optical antenna systems, which are used for different applications, for higher frequency, millimeter. So there are various. So with this, we are able to improve the resolution on the ground. It's called sensor is like an eye in a sky, from where you are able to see on the ground. These are the images taken from a microwave radars, as well as our ocean can also be covered like that with we can see the winds, ocean winds with the microwave radars. So similarly for navigation, again same concept. I will not go into the detail. So I will only say that these are also one of the area now picking up. Lot of applications are coming from navigation for Indian satellites. So I will concentrate only on antenna. So I will first talk about array antenna. Array antenna, when the moment it comes to everybody's mind is that the array means it's a number of radiators which are arranged in a particular lattice. But that lattice, normally we talk about systematic, either rectangular, circular, or any particular triangular lattice structure. But now people are also working on a aperiodic or quasi aperiodic array antennas, or you can say by they are thinning the lattice and one more degree of freedom they are adding. So that's another area which is so selection of element that the lattice is very important. Then comes your the feeding mechanism. How you are feeding each element. What type of transmission line you are using. It will again depend on what type of power we are talking about. Then mutual coupling and the surface currents. Again, they are all the problem. The moment you add the complexity, the moment you want to make it more compact, more and more bands you want to add. Normally, when we talk about 0.5 lambda spacing or 0.75 lambda spacing, there is a particular fixed element gain comes. But when you want to reduce the spacing to get a large scanning without scan blindness, then your surface currents and mutual coupling become very important. Similarly, for grating lobes and side lobes, we need to have address the issue by seeing that we don't we reduce or eliminate the surface currents and come out of the mutual coupling. Okay, so I'll go to the next. So one of the this is very primitive. You see, helix array antenna is one system which people have been using since ages. If you see any old book, it will talk about. So this is the one which I have shown on the we developed one L1 and L5. The L1, L5 are two frequency bands, which are required for developing a single helix, which can work in two bands, that is 1.21 gigahertz and 1.5. These are two bands, L band. Within L band, two bands which are nearly 23% away. Now, when you want to design a helix array for either one choice is that I can make a 1-2 separate antenna array. Other is that I can make a helix which can work in both the frequencies. And then I make an array of this. So this is what the earlier patent somebody took, that he has made a tapered helix. So but we also developed one more type of helix which is called quasi tapered. We took a simple material, and the first one which you are seeing is on a X-ray film we had, and one of the chest X-ray report we had, and we simply made a tapered helix. But then you see novelty that we have come out with a much better results in terms of by reducing the impedance, or you can say the currents at the tip of the helix zero, and so that our axle ratio is one of the very important specification for any helix antenna, that is circular polarization of the order of 0.5 dB. So here we were able to achieve by not only by the helix tapering, but also by impedance matching. So at the tip and at the input, all the impedance were matched, and very standard way. You see the 4x4 array, 2x2 array in a normal rectangular helix, but you are seeing some cups are sitting in the back side. These cups were reduced to, they were of some special material, the carbon fiber, so that that was only required because of the lightweight. But actually, you need a perfect electric conductor there, so that you need a metallic wall, so that you can reduce the surface currents can be reduced, and they don't couple with the ray tracing and all that we do, so that we know where are the hot spots, and by placing this, where we are able to reduce the surface currents on the panel itself. So we are able to do that, and we test them together. And this was one of the two patents which we took, one in US, one fine work with my team, and we did here. Another one is now earlier it was 2 L-band. Now it's ISRO, when they started the IRNSS program, there was hardly any band left for. We could not get any other band. Only L5 and Xband was available. That is, so new Xband was new to any service provider. So we have to make a now new type of antenna, which can cover the two distinctly different bands, L5 and Xband. So we came out with a circular array because of two reasons. One is because of course, symmetrical radiation pattern. Other is because of there was a very typical requirement of phase center. They wanted a concentric phase center. So this was also one of the typical requirement which we met, and then we measured the phase center in the anechoic chamber, and we could get the accurate this position of a phase center. Okay, now I will be, this is the one new technique which we established, and this paper came in IEEE magazine, AP magazine in 2017, and it covers about this. Now the new future, now where we are, if you know that you are following ISRO, then you will see that nearly up to IJ is going to be launched now, next satellite, which will be having a 3 bands, maybe I think beyond that, 1J beyond. So that will be, we are talking about now all the 3 bands, L1, L5 and S-band. So now it becomes all the more challenges, because the transmitter and receiver systems cannot be very broadband. Because there the power requirement, power stability and the flatness and the noise temperature of the receiver is very important. So the availability of devices, the P-ham devices or ham devices, or for that GAN SSPAs and all those things, availability is the issue for wideband. But antenna, you have your own innovation. You can design, because if you don't need any foundry, you indigenously you can design 3 bands into a single antenna, and this is a new complex which, and then again talking about the phase center requirement and high power requirement remain same. So there in the high power, the feeder network becomes very important. So that is being shown here, and we use method of movement or FEM finite element method, and we have our own codes, some of them tailor-made for the requirements. They are being used for finding out the currents, finding out the impedance input mismatch, or for the even for the ray tracing. We want to know that if we consider a high frequency, then we can use even the geometrical optics. Now, this is what I covered about the helical antennas. Now I am going to talk about planar antennas. See, this is one of the India's one of the largest. 2012, this satellite was launched. That is called synthetic aperture radar, and this was first of its kind to demonstrate that even microwave SAR can be used, which has its own advantage in terms of all time. It can be used. It doesn't need any optical frequencies, even the micro frequencies. We can take the images of the ground, or we can take a lot of information from the atmosphere or from the ocean. So this was the one typical requirement of 6 meter by 2 meter antenna. So which is right now you are seeing they are folded to 2 meter by 2 meter. So you are seeing all nearly 5,000 patches are there. Now each patch is now connected to the another patch with the feeder network, which is electromagnetic coupled, and then each linear array is having a transmitter and receive module. Why we need to do that? Because we need to scan this beam in azimuth and elevation direction. While satellite is moving in one plane, one track, the beam has to see in a different direction. So scanning requirement comes to picture. So that's right now video is not working because I converted this file to PDF. Otherwise, you would have seen that how the different elevation as well as azimuth plane beam steering is required. So some is be taken care by the satellite, some is taken care by the electronically phase array antenna, that by changing the amplitude and phase. So this is the one of the typical example of a multi-layer antenna, which a lot of papers I am seeing nowadays in the PhD students are doing a lot of innovation in that. So this is electromagnetic coupled printed antenna, and we get the advantage of both large bandwidth and high gain by reducing the dielectric constant very low for our antenna radiator and very high for our microchip feeding network. And the wideband performance is being achieved by designing a. When I say wideband here, normally patch is known devil for a low bandwidth. But when I use a wide bandwidth performance for a microchip, I say 10% bandwidth. But when I talk to waveguide and all those things, I talk about wideband 35, 40%, 50% bandwidth. So here I am say wideband means something like 10% or 12%. So this was you can see one typical view of a linear array. There are 20 elements, and to compensate the cross polarization being generated from the transmission line itself generates the cross polarization. So the cross polarization compensation technique is being used, which is will take care of the cross polar performance will be reduced. So this is a very typical example where we are, and each this is the backside of an antenna, 2 meter by 6 meter. At the backside, we are having a nearly 576 transmit and receive modules, which will all get integrated and will be controlled by a controller, which is going to control basically the phase shifters, attenuators, as well as required for each beam. So then there are power control systems, power dividers, and antenna and panels. Recently, you must have seen Chandrayaan-2 became very popular, but because of the lander. But there was the orbiter also was there. Orbiter, Chandrayaan-2 dual frequency synthetic aperture radar was there in the orbit. Still, it is working. And this was a very, very difficult design we had till that time, when we were asked to build 4 types of application into a single antenna, wherein this can be used for L-band SAR, synthetic aperture radar, S-band synthetic aperture radar, and then for communication while it is in the orbit, not even gone into the orbit of a lunar. It was being used as it can be used as for a telemetry and telecommand for getting the information health of a satellite. So for making this was the first unique synthetic aperture radar ever flown by any of the space agency, because earlier they have flown only single band SAR. NASA has flown single SAR, that is called mini SAR. But this was a dual band SAR. Lot of applications were there, and the mass constraint was there. So I will show you. So this was the concept where we have used a shared aperture, and you're seeing this white color at the aperture. This aperture is basically white thing is nothing but a foam. Foam normally we use, which in our packing material. So this is a particular RF foam which can be compressed, and we have machined wherever it is not required. So very different, where we are having L-band SAR, S-band SAR, and lander communication also. So this was got a best research-oriented paper in 2019 by IIT, a CDL award for industry, which we got. And our engineers, they built a lot of challenge by there. We reduced almost 7 to 8 kg mass by reducing all the unnecessary material which is not required, but because of which a lot of changes were required in the design and analysis. So this was a 10-layer antenna. So that was one good example. Then we are also having you come across so what I am trying to tell you is that there are various requirements which are coming for the future of our wireless systems or any type of sensor. You need to have multi-bands. You need to have a high power. You need to have a high power, low losses. And then cross polarization becomes a very, very important, because I am reusing the frequency in the 2 planes, 2 polarization. Suppose there is a KU band. I am using KU band vertical polarization for one type of communication, and the other one is in a horizontal polarization. So I need to have an isolation. Otherwise, both the signals in the same frequency band will be have a tendency to mix and will make sure that nothing works. So need to have a 30-35 dB cross polarization between the vertical and horizontal polarization. So sometimes you need to have a pencil beam, sometimes you have to give a sector beam, slope sector beam, you need to get cosecant scale beam. So these are all typical examples of that which we have worked for the various applications. I will not go into that. I will come directly to shaped beam antennas. And right now, whatever I talked is only the array antenna, the multilayer antennas, okay, the patches. We also use dielectric resonators. We also deployed at low frequencies, we have used air itself as a dielectric, and use a cross dipoles. So various types of array. But now I am going to talk about the reflector antenna technology, because as I was telling earlier, the shape of the beam is very important. The shape of the beam which is required to the way we look from the satellite, the eye from that angle, which portion we need to cover while we are covering the satellite coverage area. We call coverage areas. So coverage area is basically decided by the shaped beams, if you want to shape it. Otherwise you will get like one which is shown here, the UHF global. It is a circular concentric beam. Otherwise you are seeing, now this is a very interesting thing where we got a SARC, all SARC countries were to be covered by a single satellite. We need to cover the Afghanistan, the Nepal, the Sri Lanka, the Maldives, and our neighbor, the Pakistan also was to be excluded, because so there was now you need to have a corrected null in that area, and you have to generate a beam of that type of so that we are able to give a proper communication between these all countries. This was happened only in some 3 years back. So all these requirements, how we can do? There are various ways. I will not touch the technology, but what I will talk about theory. Theoretically, if you see, we need to, the moment we disturb any symmetricity of a antenna radiator, that means then only I will get the shaped beam. I don't need a pencil beam. But then when the moment you do that, the cross polarization goes very bad. Your side lobes will become very large. So how to control those? So we need to shape the beam, or we do or a pencil beam, whatever we are having, we have to fill the nulls, and all the side lobe peaks we have to increase. Instead of decreasing, we have to increase, so that I get a very wide beam. And wherever I don't need those regions, I have to again ensure that my aperture distribution is such that my antenna is not giving any radiation pattern in that direction. So geometrical optics, physical theory of diffraction, geometrical theory of diffraction, all are used for this type of technologies. Okay, so I will give you one very good example. This is a single reflector technology, where with a single reflector we are able to give a shaped beam. We are able to give a pencil beam in one direction, and in another case a very, very large sector beam, nearly 60 degrees. So plus minus, you can say something like a 0 degree to 30 degree in one plane. And also we need to talk about cross polarization. You see the cross polarization here, the energy in the other plane is something like 35 to 40 dB. So this was by shaping the reflector, and this is the way we are testing in our antenna test range, where we do the anechoic chamber we do the measurements. And then this is another one good example of this is a very good example, center one, which you are seeing here. There is the two beams you are seeing here, with a large beam width and a smaller beam width. You know why it came? Because I want to give this is area where our sea region is there, and these are our Andaman and islands. So we wanted to cover the Indian region as well as the islands. So we were supposed to cover that, and we got that antenna and beam. So then GSA-17 was another example where the beams, side lobes were to be controlled over the total globe. Some of the small countries, small regions, where we need to give a very, very small power, that was to be reduced. So that was done. Similarly, the dual graded reflector antennas. This is now you see the shaping. Here the parabola normally has a very parabolic shape, is well known. But here you see the reflector is shaped in such a way that we are able to control the radiation pattern as per my requirement. So these are the various examples when we do the scattering analysis. When one antenna is mounted on one spacecraft, how it is interacting with the spacecraft body as well as with other antennas. So this is what we've seen, and then we ensure that no deterioration or on the side lobes as well as on the cross polarization. So these were the various. You can see we took some 4 patents here, and one of them is on generating 2 different types of beams simultaneously, the contour beam and pencil beam, from a single shape reflector. So there are various techniques. I think the innovation can be done unless until we have a challenge, unless until the challenge is imposed on us. So we cannot go for any innovation, and that's the key success of any society who takes the challenge. So here I am now in few slides. I will talk about the feed technologies. I will not go into the details, but I will talk about various complexity, the technologies are required for multi-mode, multi-band antennas. Reflectors are wide bands, okay, but the multi-band and multi-mode or high power requirement come from the feeds, which feeds the antenna, the beam efficiency, the duplexing network, the frequency selective surfaces, multipolarizations. So by controlling the modes by solving the Helmholtz equation in a waveguide and then calculating the modes and then appropriate amplitude and phase of these modes, we can control the radiation pattern. So these are the various techniques which are being used by mixing different types of mode to control the radiation pattern, and also with a 0, or we can say minus 40 dB, minus 50 dB cross polarization. So there was one very good requirement which came from one of the multiple beam antenna. The moment the antenna beams become very narrow, what happens is the beams are size become very small. Then you need to have some tracking system. How to track the beams, because they are so small, perturbation will deteriorate the whole signal link will be disturbed. So we need to have a tracking feed. So now you can't have a one mode. Normally everybody knows that now tracking feed means 4 horn, the monopulse. So but what we developed for this particular case, we developed instead of 4 horn, we developed a single horn, and with a single horn, by generating different modes, we are able to get a tracking modes which are able to correct the azimuth and elevation errors and crosstalk between the modes, isolation between the modes. And these were the various schemes which were implemented, and it is still there working in space for GSAT 11, GSAT 19. And same technology is can be used for ground systems also. So this was the one which we developed for ground system. One of the KU and Ka band. These are again 2 bands, but KU and Ka band. The DBS is a direct broadcast satellite band that is called Ka band. So these both bands were having a various functional requirement came where you want to track also and generate lot of polarizations, all set of polarization. So this is the one way of having a multi-mode horn, multi-mode feeds, multi-port duplexer, multi-port tracking feed, which gives you if anybody is interested, let him know, can contact me, I can give the details. And we are having a lot of now other technologies also, like for Indian data relay satellites. Now, when we are talking about Gaganyaan, we are talking about many other many other missions. So we need to have one satellite at different layers. One in the low orbits, and another in the higher orbits. So that each communication can happen between the satellites also. So this is one of the Indian, that's why it is called data relay, Indian data relay satellite. So for that we are developing currently KU or Ka band and S-band, again 2 bands, you see. Everywhere we are now having a challenge of adding 2 bands or 3 bands, which here we are using the frequency selective surfaces. Those of you who are in microwave will be knowing that a lot of work is going on a dichroic surfaces. So that is being used as a reflector. So it is acting as a space filter. So it is separating or rejecting one band and accepting the other band. Now other one application I'll quickly cover now, maybe another 5 minutes. Then can be open to the question answers. That is the Xband. Xband. I don't know. This video is not working. No. So these are the unfoldable antennas. So same unfoldable antenna which can be stored on the spacecraft when it is kept on the launch vehicle like this, and when it's deployed, it gets deployed with this X-band, F-band. Now we are planning to have a higher bands, and then with the multiple beams, So this is the one which is now going to be the world first dual frequency SAR, that is synthetic aperture radar, which is the 2023 it will be launched, and sometime it is a joint mission between ISRO and NASA, and wherein the feeds are where we are going to use the new concept called sweep SAR. We will be achieving the high resolution without degrading the swath. So this is having a 12-meter antenna. A lot of new technologies like Xband. This mission is going to have Xband SAR from ISRO and L-band SAR from JPL. So there again we are having a two bands radar. So we are having a multiple very narrow beam from a 12-meter antenna, and there are 24 feeds in the focal plane. A lot of because of which we are able to see we get a large swath, and then by transmitting a very miniaturized transmit and receive modules, we are able to get a signal, and that how high out the signal which we are getting in the synthetic aperture radar is being transmitted back on the ground at a very high band, that is K band and beyond. Because now the data rate is requirement become very large, so we need to dump the data on the one of the ground station on the ground before it moves to the Indian station also. So in which is lying on Indian region. So these are the various technologies. So we developed on the US aircraft, we developed our antenna technology for imaging from the aircraft. So this is now there in US. So we have developed antenna as well as the technology for them. These are the images which has come. And the last slide which I am showing here is of the millimeter wave technology, which is now, we are now going to the higher frequencies. We are talking about optical frequencies. We are talking about 60 gigahertz, 110 gigahertz, 220, 300 gigahertz for various applications. Of course, we can't solve all the frequency band. We cannot solve because their attenuation is very high in this frequency band. But that we say that even though the attenuation is there, but we are able to use that information of attenuation for atmosphere mapping of the atmosphere. We can give lot of information of atmosphere. Wherever we get a large attenuation, we are able to give the mapping of the vertical column or the wide coverage. We can cover from the satellite using this frequency band. So these are new areas which are coming up. We need to develop antenna technologies, the feeder technologies, the receivers, the transmitters. So a lot of scope is there, and if anybody is interested to work on this area, not only what I covered, but in any area where you are interested and you think that ISRO has a common interest, you please see our website, and you can see. We have a response document. You can go and see, and from there you can find out what we are interested in. You can send a proposal to us, and we can definitely look into it and see that we can use the potential which is there with our academic institute. I think there I will end, Dr. Kundu, and maybe I'll open for questions if any. Over to Kundu. Thank you.
Thank you, sir. Thank you very much for this very beautiful and informative session. Indeed, we enjoyed a lot. So I see earlier that there was a lot of appreciation messages and questions in the chat box, but unfortunately I was disconnected in between for a few minutes, and I lost all the queries. So the participants, if you are having a query, you may please type it in the chat box, or you could unmute yourself and ask directly. Okay, sir. One question I got from the participant, which is, among satellites, meant for a same application, how is interference mitigated from other antennas?
So the interference can be mitigated because with the three waves actually. One is like on ground, similar applications, similar wave. Like in ground, what we do, we try to reduce the side lobes so that it doesn't see the same area from where the interference is coming. We can reduce the gain of the antenna. Second thing is we can change the polarization of the antenna so that even if it is same frequency signal is coming, I can change the polarization. And the third way is that we can even by spatially keeping, normally for any satellite when we keep in the orbit, we keep nearly 1 degree separation we keep, which amounts to large distance, 1 degree in subtended angle I am talking. So that itself is able to, because the ground station antenna which we are using, they are having if they are having a wide beam, then they are seeing all the satellites. Normally that happens for a small size. So it's not only the communication satellites or navigation satellites are interacting with each other, even the ground stations beams are also, so the architecture or the configuration of any network, but before we conceptualize, has to see that all things are embedded into the system. Otherwise, what will happen is one satellite gets launched, then its only question is that you have to mitigate the problem on the ground by using ground technology only. So you have to analyze all the scenarios well in advance so that you are aware of wireless. Like I'll give you one example. One of our some earlier bands which was meant for radar, now it is being used for our wireless LAN. So even though the wireless LAN is having maybe something like a 3 to 4 dB gain, and in the direction of a satellite it will be very less, and the power also is going to be very small. But definitely it can interfere even with the cross polarization signal. That is, that noise floor of the system becomes very large and get affected. So these are the things which we have to solve earlier. 1 minute. Yeah, please go ahead. If you have any other questions.
Yes, sir. Yes, sir. So we'll be taking 1 or 2 more questions, sir. So the next question is, how did you make the antenna pattern similar to the map of Indian map? Did you use pattern multiplication for that, or is there any other method?
Yeah, please. Can you repeat the question?
Yes, sir. The question was, how did you make the antenna pattern similar to the Indian map?
Yes.
Did you use pattern multiplication for that, or is there any other method?
Yeah. I think it's a pattern synthesis method. See, like null perturbation methods are there. Na? The people, the Eliot has given in his paper that how to use in a single array, single linear array. If you want to give a shape pattern, normally you will get the conventional pattern with lot of side lobes, and if it is a Gaussian beam, you will be getting all the side lobes reduced to some systematically it will be coming down. But then what he has done is he has used a method in which the nulls are filled, as I was mentioning earlier, and the peaks are increased, and that how it is being done by again synthesizing aperture distribution of the amplitude and phase in such a way that we are able to get the this radiation pattern of the shape that we want. So this is a basic concept, but now how to use this, there are different ways. Some are using physical optics techniques, then some people are using a Fourier transformation, and then signal processing we are using, or some people can use even the, as I was mentioning, null perturbation method.
Right, sir. So, Dr. Trilochan Panigrahi asked that, is there a tolerance limit interference power in satellite communication?
Is there
any tolerance limit for interference power in satellite communication?
Yes. No, that is true. We call it flux density. the flux has to be kept same to the level that it has to be kept into a level what is permitted by ITU regulation. So we cannot increase the power flux. It's because it can interfere with ground communication as well as the not safe for the so per bandwidth per hertz how much you can send the power, the flux that is being seen as a one criteria. We always adhere to that.
Right, sir. So I could see appreciation message from Dr. Mahadevan, ISRO, and I'll be taking one more question. Sir,
Dr. Mahadevan
Dr.
is my senior, and I'm sure
right.
that I'm very happy that he is there. Sir.
Sir, Rajesh Jyoti, wish you all the very best. I could see the SAR payload being just rolled out and then sent to JPL. Only
Yes.
one thing I want is are you using, who is making the antenna, NASA or ISRO?
Yes, I think it's very good. See here, you know that what we built is 6 meter and 3 meter antenna for our RSat Xband satellite and for our GSAT 6. The 12 meter. This is the 12 meter antenna which is made by Harris.
I see. So that same antenna will be used for both S and X.
Yes, same antenna will be used with having a L and S band feeds at the aperture.
So the feed is made by SAC?
Yes.
Oh, very good. It's an excellent payload and we are really looking for the dual band operation.
Yeah.
So wish you all the very best.
Thank you, sir. Thank you, sir. It's all because of
nice hearing.
The foundation you people have made, sir, at that time.
Thank you so much, and so happy to hear you because after a long time hearing your lecture.
Okay. Thank you, sir.
Thank you.
So the next question I would like to take that is asked from Dr. Gopinath Samanto. What is the scope of terahertz antenna in communication industry?
Terahertz in communication, as I said, there is a for 60 gigahertz and all that we are using it for our satellite to satellite communication, where the attenuation is or the speed, the spreading loss is less because of the otherwise. They are being used for only the people are trying even for when I'm talking about terahertz. We have before we go to terahertz, some millimeter antenna is the one area where we talk about what is their application before we go to terahertz. So even 60, 110, and these are the new area which people are now talking about for 5G and beyond 5G next application. But for these particular bands, which are, as I said earlier, that they can be useful for even for astronomy, for beyond higher bands, because lot of oxygen lines, carbon monoxide lines, which are there, because they have a particular pattern. So for Cosmo studies as well as for our atmospheric studies, these frequency bands are very, very useful. It gives a lot of insight which we are not able to get at lower frequencies. But definitely for terahertz, if you ask me, no, this is right now, people are only using for radar imaging like our X-ray scanners at the airports. A lot of work is going on that it can go see through, or for medical science. People are using for even for getting a heartbeat of a person who is traveling, moving in a crowd. You can see that whether what biomedical parameters he is having. So those type of applications are there, but not in communication. I didn't see.
Right, sir. So there are a couple of questions on MIMO antennas. The Snehashis asked that can the active elements be used in MIMO antenna? Any real example, sir?
Yes, people are using it. Rather, it is being used. A lot of papers are coming up for terrestrial communication as well as for tactical communication. People are using it. So I am not the right expert on talk on that.
Right. Okay, and sir, Ajit asked that what are the industrial applications of UWB MIMO antennas?
So there are a lot of applications because, like I tell you, the retro directive type of application where we once the radars are being, we know that signal is coming from one particular direction, and we don't know which direction it is coming. So we can identify the direction. So we get lot of inputs, antennas are there, and we do. Then from there, they are again using a radar and using sensing the signal, and then do its own. That's for tactical. So this is all being used for multiple applications. But commercially also it can be used for our terrestrial communication and wherever crowding of the bands are being done. Even for 5G and all that, also people are trying to use it.
Right, sir. So thank you very much, sir, for all the efforts, all the time, for sharing this very beautiful and informative lecture. So on behalf of the workshop organizing committee, again I express my sincere gratitude to you. So thank you, sir.
Thank you, Surajit. Thank you, Mahadevanji. Thank you, everybody, all the participants. I enjoyed your questions were very. From that itself, it looks like most of you are attending the lecture. Thank you very much.
Thank you, sir. Jai Hind.